Okay, welcome to day 6, differential equations and applications. The last 2 weeks, we basically have been taking derivatives of real-life situation called related rates to figure out problems. We're going to do we're going to do something different today. We're going to use calculus, but instead of doing derivatives, we're going to use something else. So, I'm going to take today's notes. We're going to talk about differential equations. We did these before. We've been taking f prime or y prime or dy dx. These are all the derivative, also known as the differential. So what we want to do is we want to do the undo of this, and that is the anti-derivative. And if you recall, we're going to use this symbol called the integral symbol. Okay? So in other words, if we take the antiderivative of the derivative, we should get the original function. And don't forget, there's always a plus c. We've done this before. We'll go through some examples before we get into doing the real-life applications. But the whole idea is that we're taking the antiderivative. So if you recall, we've done problems like this before. It says the derivative, or the differential, or the dy over dx, is equal to 2x cubed plus 4x. We're going to bring this over to the other side by multiplying it over. I have dy is equal to 2x cubed plus 4x dx. The dx is just the variable of interest. How do I do this? I take the antiderivative. So the antiderivative of 1 dy, or just dy, is y equals, and remember when we take antiderivative, we add 1 to the exponent. So that's going to be x to the 4th, and then I use that reciprocal. So the reciprocal of that is 1/4 times this number 2 here. I get 1/2. And then I'm going to keep on going on. This would be x to the first becomes x squared. Reciprocal of 2 is 1/2, so I do 4 times 1/2. I get plus 2 x squared plus c, and I'll write it neater. Y equals 1/2 x to the 4th plus 2x squared plus c. What's really nice about all this stuff, you could go ahead and take the derivative of this problem, and you should get what you had in the beginning, and you do. So again, I have my derivative is equal to some function that uses x. I'm going to bring this over to the other side. I'm going to rewrite this problem as dy is equal to 8. I might as well rewrite this as x to the 1/2 minus 2, and it's got a dx over here. So what I want to do, I want to take its antiderivative. So y equals, well, I got to add 1 to this, and I just do top minus bottom, or 3/2, and the reciprocal of 3/2 is 2/3 times 8. I get 16/3 minus 2x plus c. That is the general antiderivative of that differential equation. Again, you can always take its derivative and see if it works out. So now I'm going to do the same idea, except I'm going to have some initial value to help solve for the c. So I'm going to use this point, which is 1, 10, to solve for what the c value is. So it's not general anymore, it's a specific. I'm going to bring the dx over to the other side. I'm going to take its antiderivative, and I get y equals, well, 3, excuse me, that's bad, 2x to the 3rd plus 2x squared plus c. And now I could plug in 1 and 10 in for the x and the y. I get 10 equals 2 times 1 cubed plus 2 times 1 squared plus c. 10 equals, I get 2 plus 2 plus c, or 4 plus c, and I get c is equal to 6. So I can rewrite this as y equals 2x cubed plus 2x squared plus 6. That is the specific solution to the problem I have in hand. Again, you could take this derivative and you would get this initial dy over dx differential. Okay, we have another example. Instead of having x's and y's, we have ds and dt. Doesn't really matter. T is the input, s is the output. I'm going to bring this over to the other side. I'm going to take its derivative, antiderivative. And I get s equals negative 16t squared plus 100t plus c. Now, my initial condition is that when t was 0, s was 250. So order pair of 0, 250. I love plugging in 0 for my input. For most of these examples, it makes life really, really easy. We're going to plug in 0, 0, didn't really change color. I'm going to plug in 0, 250. You get 250 equals negative 16, 0 squared plus 100, and 0 plus c. And I think you can tell right away that these all go to 0, and you get c equals 250. So s equals negative 16t squared plus 100t plus 250. Okay, another example. Again, I'm going to bring my dt over to the other side. I'm going to take the antiderivative. So I have dv over dt has been rewritten. My input's t, my output is v. So I have v equals 3t squared minus 4t plus c. This is my general antiderivative, but I do have specific points that I could plug in. I could plug in 2, 25 for the t and the v. 25 equals 3 times 2 squared minus 4 times 2 plus c, or 25 is equal to 12 minus 8 plus c, or 4 plus c equals 25. And I get c is equal to 21 if I want. And then I can rewrite this as v equals 3t squared minus 4t plus 21. That is the specific solution to that initial problem of the derivative is equal to 6t minus 4. It's not that difficult. It's just kind of undoing what we've been doing for the last few days. So how are we going to apply this to real life situations? Well, one way is to look at these three values called displacement, velocity, and acceleration. Displacement is a little bit different than distance. Displacement is your change of position. Velocity and acceleration. And since this is math class connected to physics, displacement, velocity, and acceleration can be positive or negative. Measurements for displacement are things like feet and meters. Velocities would be like feet per second, meters per minute, and acceleration would be feet per second squared, meters per second squared. Those would be its measurements, and as you could tell, displacement is a length, velocity is its derivative because it's a rate, and then acceleration is the rate of the rate. So when I have displacement, I call that s, And if I take its derivative, s prime is equal to velocity. And if I take its derivative again, s double prime is equal to v prime is equal to acceleration. That's a relationship in physics that we use with calculus, is that my displacement is my position, its change in displacement is called velocity, or s prime is equal to v, and that second derivative of the displacement, or the first derivative of velocity, is its acceleration. So how do we work backwards? Well, this is interesting to see how we can work backwards, because that's what we're going to work on today. If I have acceleration, and I want to take the antiderivative, well, what do I get? I get that the velocity is equal to the antiderivative of acceleration. And if I take another antiderivative, I learn that my displacement s, or distance, or whatever you want to call displacement, is the antiderivative of velocity. So this is what we're going to work on today. These ideas. That displacement s, s prime is velocity, s double prime or v prime is a, or in reverse, the antiderivative of acceleration is velocity, and the antiderivative of velocity is your displacement. Okay, this top half in the orange box is a summary of the previous page, using the idea of displacement, velocity, and acceleration, using either derivatives or antiderivatives. And for this class, not in real life, not for physics, not for AP physics, but for this class, just to make numbers easy, when we talk about gravity, about vertical motion, things falling down and being thrown up in the air, acceleration for gravity is negative 10 meters per second squared, or negative 32 feet per second squared. Okay, my example is a tennis ball is being thrown upward from a roof that is 55 meters above the ground at 50 meters per second. Let's give the formulas for acceleration, velocity, and the height at time t. Well, my acceleration is just gravity, and acceleration is going to equal to negative 10 meters per second squared. I will include the units on this now. But now I want to find velocity. Velocity is going to be the antiderivative of acceleration. So that is just the antiderivative of negative 10 dt, because I'm working with time t as my variable. So my velocity is negative 10t plus c. Let's see, do I have an initial condition? Yes, I do. I have, at the very beginning, at t equals 0, I have an initial velocity equal to 50 meters per second. So I plug this in, v equals negative 10 times 0 plus c, and that gives me a result of c is equal to 50. So my velocity equation is negative 10t plus 50. Now I have to go to figure out my height, or my displacement. Instead of calling it s, I'm going to call it h for height. Well, that's going to be the antiderivative of velocity, which is going to be the antiderivative of negative 10t plus 50, again, dt. So h is equal to, well, t becomes t squared, so it's negative 5t squared plus 50t plus c. Do we have an initial condition? Absolutely we do. When t equals 0, my initial height is 55. That's how high it's off the building. So 55 is equal to -5 times 0 squared plus 50 times 0 plus c. And then obviously those are 0, so you get c equals 55. So my height equation is going to be -5t squared plus 50t plus 55. So now I have all three equations. I'm going to use those to solve the rest of the problem. Okay, continuing this problem for part B, it says, how high does the tennis ball go and when does it reach its highest point? So I want to figure out what is its max height and what time on the clock does that happen? Well, I talked about velocity being positive or negative. Velocity is positive when things are going up in the air, and velocity is negative when things are going down in the air. So when I'm at the max right here, its velocity is equal to 0 because it was positive velocity going up and then negative going down. So right at the max, its velocity is 0. So I'm going to take my velocity equation, set it equal to 0. And I get for my time at t equals 5 seconds, that is the time that the ball is at its maximum. So I'm going to use that in the h equation and say h of 5 seconds is equal to -5 times 5 squared plus 50 times 5 plus 55. A whole lot of 5s there. I plug it in, and h of 5 is equal to -125, 250. I get 180 meters. It's its maximum height. So when this ball is thrown up at 5 seconds, it reaches a maximum height of 180 meters. I don't know if this was the person throwing this. That's pretty high. How long is it up in the air? Well, I'm asking how long does it take before it hits the ground? Well, when something hits the ground is when the h is equal to 0. So I'm going to take my height equation. Say 0 equals -5t squared plus 50t plus 55. I can put in a calculator. I'm going to try to factor it. I don't like factoring out -5t. I see they're all can be divided out by -5. So I'm going to divide everything out by -5. I get 0 equals t squared minus 10t minus 11. And then I try to factor it. I get 0 equals t minus 11 and t plus 1. So I have two solutions for t. My two solutions for t are t equals 11 seconds and t equals -1 seconds. And we all know you cannot go backwards in time. So my solution is it hits the ground in 11 seconds. So I want to know its velocity when it hits the ground. So I'm going to plug 11 seconds into my velocity equation. And I get v of 11 is equal to -60, and its velocity, in this case meters per second. So when it hits the ground, it's going pretty fast. -60 meters per second. So this is how I use calculus to figure out this problem. Okay, so I'm going to have to be able to work through some word problems. So again, more word problems. A car goes from 0 to 60 meters per second in 10 seconds at a constant acceleration. That's the key, constant. That means my acceleration is the same the whole time. So that's change of velocity is change of t, which is 60 minus 0 over 10 minus 0. And I get my acceleration is equal to 6 meters per second, or per second squared. The idea that it's constant is the key. I could approach it as something linear, or that it has a slope. And that's what I did. Change of y over change in x, in this case change in v over change in t. So I'm going to draw a graph. So I have a car that stops in 5 seconds, and it takes from 50 feet per second. So here's velocity in feet per second. Here's time. This is 5 seconds. This is 50 feet per second. And I can't use a straight edge, but I'm going to do the best I can. Imagine that is a line. So this idea of being constant means it's linear. That means this slope here is the acceleration. So A equals change in V over change in T, which it goes from 0 minus 50 over 5 minus 0, or negative 50 over 5. So this acceleration is negative 10 meters, excuse me, I don't know why I did meters, feet per second squared. So that's what that slope means, because it's a constant. Then it says represent as an area on the above graph the total distance traveled as time breaks. Well, if you remember from your physics class freshman year, you figured out that when you did this area right here, this area here represented the total distance. Okay? I'm gonna move it up. So here we go. I want to figure out this total distance. Well, I'm lucky. I got a nice right triangle. So area of a right triangle, I have a nice right triangle. And area equals 1/2 times base times height. And for this triangle, area is going to equal 1/2. The base is 5 seconds. And the height is 50 feet per second. And if I multiply this all out, and I get to see that the seconds here cancel out the seconds here, my total area is 50 times 5 is 250. Half of that is 125 feet. That is the total area of that it took for it to stop, or that orange area there. That's using geometry. That's not using calculus. We're going to use calculus to solve this problem now. So I'm going to use calculus now. What do I know from before? I know that my acceleration is equal to negative 10, and at t equals 0, my velocity is equal to 50, and my distance, I call it d for displacement, is equal to 0. I haven't gone anywhere yet. Well, let me use my calculus skills. So I'm going to scroll this up. So I have all this area to do. And change the color. Well, velocity is equal to the antiderivative of acceleration, or negative 10 dt. My velocity is equal to negative 10 t plus c. I'm going to use my initial condition of 0, 50. I plug it in, and I get 50 equals negative 10 times 0 plus c, so c equals 50. So my velocity equation is negative 10t plus 50. And then I know my distance, or my displacement, is equal to the antiderivative of velocity, which is my antiderivative of negative 10t plus 50 dt. And so d equals negative 5t squared plus 50t plus c. I have an initial condition of 0, 0. I plug that all in. I get c equals 0. I'm going to move this to the side. And I have my equation is now d equals negative 5t squared plus 50t plus 0. And I have for t equals 5 seconds. And I plug in 5. I get negative 5 times 5 squared plus 50 times 5. And I get my distance is again 125 feet. So it works both with geometry and calculus. It's easy to do geometry when you have a nice right triangle. Maybe later we're going to do things that aren't nice geometric shapes. Okay, those are the notes for today. Thank you very much.